Hello and welcome back to our reading of categories and sheaves. Last time we introduced the basic notions of category theory. We said what categories are. We gave some examples and some of the most useful adjectives that one encounters when describing categories. Today we're going to introduce the notion of a morphism of categories. This is embodied by the definition of a functor. So let C and D be categories. A functor, which we'll usually denote by F, capital F, will be represented by something C to D, consists of some data. It's a map, which we also denote by F, from the objects of C to the objects of D, as well as a family of maps, also called F, from Hom in C of any pair X and Y in C to Hom in D between the image objects with the properties that F of the identity map on any object is the identity on the image object, and two, F has to be a sort of homomorphism of I don't know how to say this, a homomorphism of homomorphisms. F should distribute over the composable F and G in C. And this gives us a sort of natural way of thinking about maps between categories. In fact, up to some business of set theory, we could even make this a notion of a morphism in a suitable category of categories. We're going to try not to think about that too hard, because in this reading group, we don't want to talk about higher categories. The goal will be to sort of avoid two categories and more complicated things than that. The important thing is just to have this idea of a morphism of morphisms in your mind. We're going to develop it more as we go forward. Another remark is that if we worked in the opposite category, we would have, instead of a sort of homomorphism, we would have what you might call an Ante Homomorphism, in which if I apply F to a composition like this, I would then obtain F of F composed with F of G. And like we said, every category has an opposite category, and it's oftentimes useful to naturally think of a category as an opposite category of something else. So when we're doing that, we'll want to distinguish between functors that kind of give us homomorphisms and functors that give us anti-homomorphisms. And when we do, we'll call these covariant functors, and we'll call these contravariant functors. A functor without a descriptor, in other words, a functor that I don't specifically call contravariant, will always be covariant. And functors that are sort of naturally contravariant come up a lot. Like the most common example, and the one that we're going to have to return to over and over and over again, is Hom, maybe in some category C, into a fixed object. This is a contravariant functor to the category of sets, where we eat some category, we define this on some category C, and we send our objects Y to Hom C YX. So this is a functor C to set, and it's a contravariant functor because the natural way that these things interact is by pullback, which is going to be contravariant. Okay, With this definition made, we can say what an isomorphism of categories is. So we'll do that. We'll call a functor f from C to D an isomorphism of categories. Again, staying true to our intuition that this is a sort of morphism of categories. An isomorphism of categories is a functor with an inverse functor G, which will go D to C, is such that GF goes C to C is the identity on C, and FG D to D is the identity on D. Now, this is an extremely natural definition, but it's really, really hard to find isomorphisms of categories in practice, even when the categories are extremely similar. Like, for example, a isomorphism of categories will have to, because of this definition, be a bijection on the objects. So if your categories consist of finitely many objects, then already if they have different cardinalities, that's an obstruction to making these categories isomorphic. I want to introduce perhaps the most important example of this phenomenon with the simplest possible categories, because we're going to return to this in just a moment to say a few more words about how this works. So let's do that. So for our example, our two categories will be the following. First, we'll introduce the category, which we'll call 1, and I'll use the mathematical boldface 1. And the objects of 1 consist of a single object, which I'll just represent with a dot for simplicity. And the only morphism is the identity morphism. And I'm not going to label the dot because that seems a little redundant. And the other category that we'll consider is the category 2. And again, I'll use a mathematical boldface 2. I know it looks like Z, but you guys will know the difference. And in this category, there are two objects, which I'll call A and B. And A and B have, of course, their own identity morphisms. And there will be a single non-identity, no, I need a pair of morphisms to make this example good. So we'll have a morphism F from A to B, and an inverse morphism G. So in particular, F and G are isomorphisms. Now, in this example, these categories, for the reasons we said, can't possibly be isomorphic as categories because the number of objects is not the same. But it's important that we make this distinction because they're not isomorphic categories, even though category 2 here contains, in a suitable sense, the same data as category 1, because A and B are isomorphic objects by F and G. So even though A and B, the isomorphism lets us regard them as the same, in air quotes, you need to be suspicious of that notion of the same, because these categories are actually different. And this is a kind of theme throughout mathematics. Isomorphic objects in mathematics don't have to be the same. And there's a sense in which this is a profound idea. Maybe those of you with some knowledge of Galois theory or topology might be familiar with this idea, that isomorphic and equality are extremely different. Maybe for those of you who don't, I'll say a quick word or two with some examples from topology. In topology, one of the objects we like a lot is called the fundamental group of a space. And the fundamental group of a space is, up to a suitable notion of deformation, the group of loops. It's denoted by pi1 of x. So without getting into the technical details, basically an element of pi1x is a deformation class of a loop, and the way that you add two loops is you first do one loop and then you do the other loop, and since you're allowed to deform them, that's the same as sort of just going and doing the whole loop at once. I know that's a cruddy drawing, but you guys hopefully get the point. And the inverse of a loop is just the loop that runs the opposite way, because then if I go around one way and then I go around the other, well, then I could just pop open my loop and go around, and then I could contract this whole thing back to the original point. So you get something in the deformation class of the identity. There's some technical things involving making this completely precise and making it always work, but I want to just kind of use this example because I think one thing that everyone will find completely plausible is that pi1 of S1, the circle, is isomorphic to Z. And the way that you see that, at least intuitively, again, you have to do some work to make it precise, is if you have a starting point, an element of pi1 just counts the number of times I go around the circle, either to the left or to the right. And maybe we decide that going to the left is +1 and going to the right is -1. Well, then if I go around a bunch of times to the left, and then I go backwards around some to the right, they just sort of cancel out using the same argument as what happens when I do an inverse loop. And so it should be completely believable that the so-called winding number, those of you who have seen some multivariable calculus or some complex analysis will be familiar with that word, gives you an isomorphism from pi1 S1 to Z. And we could even call that map maybe W for winding. Now, the reason I'm telling you this is because I need to stress to you, and this is a great example for this to illustrate this, that isomorphisms are not equalities because an element of pi1 is a loop. And an element of the integers is a number. And I'm no mathematician, but loops and numbers don't seem like the same sort of thing to me at all. It's sort of this conceptual idea of the winding number that allows us to interchange them. But that's not to say that these are the same thing. It's that there is a sort of profound psychological trick that allows us to relate them. And so that's what's going on in a general category when we have these isomorphic objects that are not being identified, is there are ways of thinking of them as the same, given by the isomorphisms, but the objects themselves are very different. Both of these groups live in the category of, I guess, a billion groups, or maybe just all groups, whatever you like. And that category contains these representatives, as well as many more representatives of just the integers. It's just a very common group. Okay. With that in mind, though, we're motivated to make some definitions that sort of give us simpler categories in which we can work with this reduced data. And so moving in that direction, we're going to give our first definition of an equivalence of categories, which is a much looser thing. And this will be a sort of working definition. Later, we'll come back and we'll give a better definition, and we'll prove that our working definition is a consequence of our better definition. So this definition will come in 3 parts. Spoilers for those of you who already know what I'm going to say. So we have a functor, f from C to D, and we'll call f faithful if the induced map on Hom sets which I'll write this out this time, but I don't, like I said last time, I'm going to feel the need to stop writing out what I mean by that every single time. Between x and y, let me not write that there because I'm not going to have enough space. Someday, as this project goes along, I will learn how to do video editing, and I will learn how to use this tool to its maximum efficiency. For today, we get to go on the wonderful ride of learning with me how to use this. Okay, so if the induced map on Hom sets is injective. And 2, we'll say that, I don't need to write all the again. F will be called essentially surjective. Oh, whoa, I'm getting ahead of myself. F is called full. I said faithful, so now I have to say what full is. If the same map is surjective. And now, F will be called essentially surjective and this relates to the objects, not the morphisms. If for every object, I don't know, y in D, there is an object x in C, and an isomorphism from fx to y. So in other words, when we look at what f doesn't have to actually hit y, but it does have to hit something isomorphic to y. And so putting all this together, we're going to define f is called an equivalence of categories when f satisfies 1 through 3. And like I said, we're going to return to this sort of later when we have said some words about natural transformations. This is sort of our working definition. Let's take a look at our example again and see what's going on and convince ourselves that, well, it's not an isomorphism of categories, it is an equivalence of categories. So we had this guy, and then we had A and B with their loops, and F and G like so. And let's take F to be the functor, which takes dot and sends it to A. And functors, for us, take the identity to the identity. So we take the only element on the identity on the dot, and we send it to the identity on A. Now, as we said, this doesn't hit B, but we know that A is isomorphic to B. So already we see that F is essentially surjective. Now we have to check that it's full and faithful. Well, this is not so difficult, because if F is inducing this map, the only thing in consideration is hom dot and dot, which we know is just the single identity. And the image of this is hom f of dot, which is hom A, and the only map from A to A is the identity on A, and we hit that. So this map is sort of trivially injective and trivially surjective, so we've established everything we need. Okay, to continue for the day, let's introduce some kind of basic consequences of these definitions. So here's a proposition. So let's say we have f c to d, and this is let's make this a faithful functor. And let's say f x to y is a morphism in C. Then if f of f is a monomorphism, then f is. And this should seem sort of completely plausible, because faithful is a sort of injection on categories, and f is being a morphism in this category. We're saying f of f is sort of an injection also. So we're sort of saying that we can cancel injections when we have this interplay between these levels. And in fact, this completely generalizes to a proof. So let's do it. Let's say we have a pair of parallel morphisms, G and H. I don't want to introduce a lot of objects to make this complicated. So, but in particular, we just have F composed with G equals F composed with H. That's what we're going to assume. If we apply F to this equation, what we get is f composed with g, f composed with h, naturally, and this is a functor, so we distribute. And the upshot here now is that we've got this equation, f of f, we know it's a mono, so this gets us f of g equals f of h. F of f is a mono. But the upshot here is that f is faithful. And so the only way that this can happen is if g actually equals h. Because f is an injection on Hom sets. So equal objects come from equal places. But what you notice now is what we did is we started up here and we succeeded in canceling f from both sides. So f is a mono. And of course, we'll leave it to you guys to think about what happens in the dual case. So the last thing I want to talk about for today is I want to introduce some more categories from last time. That's going to be kind of a recurring theme for us, is we're going to continue to introduce more examples of categories as we go throughout. That'll be a sort of increasing use. This collection of categories will allow us to discuss the notions of subobjects and quotient objects, which we haven't discussed so far, but these things are very natural. Of course, every algebraic object has subobjects, and the first thing one wants to do when one wants to do algebra is study the subobjects and the quotient objects, so we'll have to make sense of that. But we need some machinery. So we make the following definition, and I apologize if this looks a little complicated, but we'll talk it out. So let's say we have a functor f from c to d, and we fix an object a in d. Then we define the category CA as follows. I'm going to scooch to the right a little bit. The objects of CA consist of the following set. They are pairs, x and s, where x belongs to C, and S is a map from f of x to A. And Hom in CA between two guys, between two pairs, eventually will suppress reference to all of the morphisms, but for now we're going to write this out, consists of the functions, which are just in C, Hom C, such that T is equal to f of f composed with S. Okay, so what's going on here? So we have x here, and we apply f to get to f of x. And then we have this guy S, which goes to A. And this is sort of the data of an object in this category. And so if I have two of these guys, maybe I'll put another such drawing over here. What am I doing? This goes to A. The condition that T is equal to f of f composed with S, well, that's just saying here that I have an f, and I can look at f of f between these guys, and that's this. Sorry. T, this map, is f of f composed with S. So first I have to do S to get from f of x. Is that right? I'm confused now. No, this is backwards. what I want is S equals T composed with f of f. This is why we always draw diagrams. So what have I got now? I've got S, this map should be the same thing as doing T, first doing f of f, which gets me from f of x to f of y, and then I do T. Good, so that's what I said now. That's a composition, so let's reorder this diagram just a little bit, just to make it super clear what's going on. This way, we have S, and this way, we have f of f. And now it's sort of clear what's going on. This category is a category where instead of having a category of morphisms, like maybe commutative triangles or commutative squares like last time, it's very similar sort of data, but it's been warped by the functor f, or maybe twisted if you like. So this category contains the data of a category of morphisms in a suitable sense. However, it also carries the data of a functor f, which, like I said, we think of as sort of twisting our diagrams. Okay, so this generalizes the examples from last time. Okay, so in this category, we'll say that two monomorphisms with the same target will be isomorphic if there's an isomorphism making the triangle commute. And similarly for epimorphisms in the dual category, which I didn't write down, so maybe I'll do that really quickly. We can define a category C upper A, where the objects of C upper A are again pairs, X and S, but this time S has to run A to Fx. And the morphisms do what I said before, but I'll write it down because it's confusing. These are the F's, such that T equals f of f composed with S. Okay, so let's keep going. We're going to introduce, am I in line with what I wrote before? Yes. We're going to introduce then the final definition, which is what we wanted to say about subobjects and quotients. So again, C a category, and let's set X to be in C. An isomorphism class of monomorphisms with target X is called a subobject. And dually, maybe I'll call this 1, an isomorphism class of epimorphisms this is with source X, it should be clear, is called a quotient. So first, to get an idea of what's going on here, we have then, let's just look at maybe, I don't know, epimorphisms to make life good. So we have an epimorphism, X to something Y, E, and we're thinking about this category of these triangles with fixed source and target. And so what we want to do is we want to have an isomorphism in this category. And I think I said what it was above, but I don't think I wrote it down, so maybe I'll do that. Just as an aside, or maybe even this is an important definition, if we have f, let's say y to x, and g z to x are monos with the same target, we'll call these isomorphic if, when we look at the diagram, which just takes y to x and z to x, then there has to be an isomorphism, which maybe I'll call these f and g, so I'll call this one h, making this diagram commute. And exactly the same for epimorphisms, except, like I said, we flip the source and target, so we just turn this diagram around. And this is an isomorphism in Cx. Okay, so with this in mind, let's see what's going on with this definition. And let's do this in the most classical way that we know how. Let's look at groups. And we're not going to do this with the category of groups because I know that you guys know what a group is. So I'm not going to talk about what's going on with groups. Instead, we're going to do a different notion of a group. And this is a useful thing to do in category theory. We can think of a group as, maybe I'll say is, a category with a single element I like to denote this element by star, and a morphism star to star for each element of the group. At least if I was thinking of this group as a classical group. In other words, every morphism, to be completely precise, is an isomorphism. So they all have inverse elements, and the definition of a category assures us that there's, for example, associative and such. So this is the same thing as a classical group. And the sort of composition rule for how you put these elements together is just what you would think of classically as the group multiplication. Let's then, using this example of a very simple category, let's see if we can figure out what's going on with these definitions. So what's a subgroup? Well, we said that this is an isomorphism class of monos in this category. So we have to figure out what's going on here. Well, classically, a subgroup is a group H together with an inclusion map into G. I'll give it a little hook because it's an inclusion. So the injective group homs are the monomorphisms among groups. And similarly, a quotient group these were just the surjective group homs. And the way that you see this is just the first isomorphism theorem of group theory. It says that if I have a map G to H, well, I can factor out G by the kernel, again in the classical setting, and obtain a map which is an isomorphism onto its image. But if G is actually surjective, then this is an isomorphism. Okay, so this definition allows you to change the subgroup by an automorphism as long as you don't change the image in the large group. And so you can have isomorphic subgroups. So this is maybe a sort of small conceptual difference where maybe you're used to thinking of a subgroup of a group as just a group living in the big group with sort of a fixed, how should I say, with a fixed image in the big group, so it's kind of defined by its elements. This is still sort of the case here, except if you're familiar with the idea of the inner automorphisms, the automorphisms coming from conjugation, then I could apply one of those specifically to the subgroup. And if the subgroup has the same image, then while the elements are now jumbled up, I've obtained an isomorphic, so to speak, subgroup. And similarly, I can compose a quotient with an automorphism and obtain an isomorphic quotient object. And this is sort of the same thing as, how should I say, maybe extending, if you like, my quotient to another group. So I have a sort of different surjective map by applying it to the coset representatives, but I've obtained, as far as we're concerned, category theoretically, an isomorphic, or sorry, the same quotient object, because our definition of a quotient or of a subobject is an isomorphism class. So as long as I stay within that isomorphism class, I have the same subobject or the same quotient. Okay, I think that's enough for today. I try to keep these videos to about 30 minutes, and we're up to 36. So I think this is a good place to stop. And next time, we'll continue in 1.3 of categories and sheaves. Take it easy.